So yeah, so let's get back to it. So it occurred to me during the break that there's a sort of an important caveat associated with this randomness assumption. So the fact that we said the black hole Hilbert space has size, the total black hole Hilbert space has size given by the Bekenstein-Hawking entropy of the black hole. And then to do this kind of analysis, we did some kind of randomness. And then you might wonder, to what extent is the black hole? To what extent does the random black hole state reflect the actual evaporating black hole? And in the context of every time you use this randomness assumption, you can ask the same question. And in some contexts, maybe the randomness assumption is good. In some contexts, maybe it's bad. But I just wanted to point out that black holes that you create from collapse of matter are almost never typical in the sense of randomness. For example, if you asked for a typical black hole state, right? In this sense, how did it form? Yeah. The way it formed is by sort of a time-reversed Hawking process, where the black hole forms bit by bit, very slowly over a very long amount of time. States, where you form the black hole quickly by collapse, are very rare. They're as rare in terms of what fraction of the total number of states they are. States that form via conventional collapse are as rare as the states which evaporate by their time reversal of collapse. But we never talk about those. We always talk about them evaporating via slow Hawking radiation.
But you could apply the same reasoning for a box. You just throw stuff in a box and you let it radiate.
Yeah.
And you would say it's not typical to just throw stuff in a box.
Yeah, sure. I mean, the air in the corner of the room example, for instance.
No, I know, but this is not true, right? If you just throw stuff in a box, that's sort of typical.
Maybe I don't know what you mean by throwing.
Make a state by just grab a box and just random stuff in the box in random order without worrying about it. Yeah. That state's typical. It will be a thermal state. And nonetheless, it irradiates by black body radiation, and it was not put together that way. I mean, because there's small correlations.
Yeah. Oh yeah, no, of course. And I mean, I think you can use the same. I mean, the question is, yeah. So there are many instances where we start the system in a state which is atypical in this sense, but its properties they're completely identical to the typical state. I mean, so the example I was going to use was the air in the corner of the room example, right? If I'm going to construct the state of the air in this room by initially keeping the air in that corner of the room and letting it go, right? The total number of states that I can construct in that way is a very small fraction of the total states possible, right? But every single state I construct in that way will behave as if it were completely typical. Okay, so that's one example where the randomness assumption was good, even though secretly, when I constructed the state, it wasn't random. So I mean, it's something to keep in the back of your head. I just thought I'd mention it. Okay, so where should we pick up? Yeah, so this is from the point of view of the outside observer. There's the horizon and the radiation, and the entanglement entropy. There's been extra lines drawn. The entanglement entropy goes like this. Okay, and there's sort of a general lesson here, which, I mean, I don't have a lot of intuition for some of these quantum information results, which show up when you study these kinds of systems. When people increasingly over the past several years, more and more sophisticated quantum information type analyses have been applied the black hole systems, this being the simplest example. I don't have a lot of intuition for these things, but one of the pieces of intuition which I think you're supposed to get from this analysis is that if you have a state in a system which consists of, a product of two subsystems, right? And one of those subsystems is small compared to the other subsystem, okay? The smaller subsystem will be nearly maximally entangled with the other subsystem, okay? In a typical state. Okay, that's one way to phrase this result. And there are ways to be quantitative about that. But that kind of situation shows up all the time. All right. Let's do a couple of thought experiments which involve the inside frame, the point of view of someone who's falling in. Okay. And we're going to try to consistently maintain that the black hole radiates and gives off information in a way that looks at least roughly like this. Okay, that if you wait long enough, when the black hole is old enough, when the entropy of the radiation starts to go down, that's when the information is coming out of the black hole. And that's what it looks like from the point of view of the outside. But at the same time, we're going to try and maintain that somebody who falls through the horizon doesn't see anything funny. Okay? And the reason why these things might be in conflict and are in conflict is because the assumption, last time, the sort of converse situation, the assumption that the person that falls through the horizon doesn't see anything funny, that's what led to this. But we didn't like this conclusion, so we're going to assume the opposite of this conclusion in some sense. We're going to assume that the information comes out and see if it's consistent for the horizon to not be problematic. Let's see, in what order do I want to do this? Yeah. So let's look at it from the infalling perspective. So again, here's my black hole. Here's someone who's falling in. And what does this person see? Well, as they're falling in, they may fall in right away. They may wait a while and then jump into the black hole after a long amount of time. Let's consider that case. So this person here, this person is usually called Alice. Okay, so what is Alice going to do? Wait for a long time. More than the page time. Then jump in to the black hole. Okay, so this person out here, they watch the black hole evaporate for a long time. They see radiation come off. In fact, you can wait until they see most of the radiation come off. And we're going to say that they don't do anything with it. They don't interact with it. But they just decide to jump in. Okay. So we're going to take the, let's give this, so this is the outside observer. So what does the infalling observer think of this system? So we're going to divide the infalling observer's Hilbert space into three parts. So first there's going to be the radiation part. Okay, this is all of the early radiation. So this is the radiation that came out before they decided to jump in. Okay, there's going to be another part, which I'm going to call B. Okay, this is radiation that's on its way out. What does that mean? It means when this person is falling through the black hole, right? When they get near the horizon, sort of maybe within the zone, they're going to pass some radiation just before they cross the horizon that is about to escape from the black hole. Sort of the radiation that's coming out as they're going in. So, I mean, we can draw that in terms of a wave packet like this. Right? So here's some wave packet of radiation that's on its way out when they're in. And this wave packet we're going to call B. And then there's another part of the system which I'll call A. And A is supposed to represent the inside of the black hole. Okay. So the person who stayed on the outside saw the stretched horizon and the membrane degrees of freedom. The person in falling, we're going to say, doesn't see the stretched horizon. They see nothing. They just fall through. Okay, but they have sort of the Hilbert space associated with the inside of the black hole. And specifically, I want to recall that there's a piece of A. If the infalling vacuum is radiation free, there's a piece of A which is supposed to be entangled with B. Okay, it's these two modes on either side of the horizon that are supposed to be entangled with each other. Okay, so is there a conflict? And the answer is that yes, there's a conflict. How do we see that? So the argument goes like this. Let's compare this with the outside observer. Okay, the outside observer sees the horizon, they see the radiation, the early radiation, and they see B. Okay, maybe from their perspective, what I called the radiation over here consists of what I'm calling the early radiation here and B, or maybe we should think of B as maybe B should be part of H. It's perhaps kind of ambiguous if B is still in the zone. But let's think of it as I'm splitting what I call the radiation into the early radiation and radiation that's on its way out. Okay. So these two factors, the two people have in common. Okay. But I don't want you to think that because these two factors are in common, that means these two factors are the same. Okay. I'm being a little bit sloppy. There are perhaps other pieces of the Hilbert space that I'm not keeping track of. The point is that the person who's falling in and the person who stay on the outside can both agree on what certain factors of the Hilbert space are. They both agree. They were sitting next to each other while they were looking at the early radiation coming out before this person decided to fall in. And when this person jumps in, they pass a particular mode B, and they're going to agree beforehand which mode they're going to concentrate on. And this person just follows, if they're allowed to use sort of effective field theory equations of motion, they're allowed to keep track of this mode B as it goes away from the black hole. Okay, so there's sort of no ambiguity there. All right. So now I'm going to cite some facts from quantum information, basically using this this same kind of assumption over here that I used over here, that the whole state is in, that there's some kind of randomness assumption, okay? And I'm going to make some statements about the density matrices on these various factors and their entanglement entropies, which I won't be able to 100% justify because I'm not familiar with, I'm not as familiar as I should be with that subject, but I do believe that they're correct. So the point is, we're well after the, so let's look at it from the outside point of view. So we're after the page time, well after the page time. So the sort of the dimension of the radiation factor, the early radiation factor, is much bigger than the combined dimension of these two factors. Sort of the BH combined system, right? The B tensor H combined system. Okay. Which is the situation where we're somewhere down here. Okay. In this case, the density matrix of the BH system, it being a very small subsystem, looks very nearly like the identity matrix. Okay, it looks like the identity operator. The state is sort of highly mixed. Okay, and in particular, if you looked for the so-called purifier of the state, so if we look at, for example, rho H, right? Okay, we know what rho H is. If we looked at rho H, right? It's some density matrix, but we asked, is there a slightly bigger factor, right? Which of this total Hilbert space, which contains H, for which the entire, for which the state is pure. Okay. What I mean, so let me write down a simple example. So if I had three systems A, B, C, and the total state psi looked like the sum of some states in A and some states in B with some coefficients, I, J, and then state C all by itself, not entangled, right? The density matrix for A would be mixed, yeah, but the density matrix for A, B together would not be mixed, okay, because it's in a product state with C. So that means B is the purifier of A in this sense, okay? So we're in a situation where H and B are in highly mixed states in this total Hilbert space, okay? Most of the spaces are, so the claim is that the purifier of H is a subfactor of R, or the purifiers of H and B are each subfactors of R, okay? I don't know exactly why this is true, but I believe it, and it seems to fit in. And okay, so in particular, we're going to make use of this RB. So now, if we identified the factor RB within R, okay, and we looked at the density matrix of rho RBB, so we trace out everything else. This is approximately pure. In other words, its entanglement entropy, rho BRB, is approximately 0. Okay, this is one fact. And we could do the same thing for H if we wanted. All right, good. So this was all nice, but we're going to take this fact here and transport it to this side. Okay. So that means over here there's a subfactor of R called RB, which is the purifier of B. And SBRB is approximately 0. Okay?
Sorry, I thought some people want to identify H with RB.
Yeah, so that's gonna come later. We're not gonna do that. So I should say the
So to probably those people argue that your assumption that RB is completing R is not correct.
some people wait. Some people want to identify H with RB.
Isn't that the case?
No.
No.
So
Sorry,
some people want to identify A with RB.
Oh yeah, sorry.
Yeah. So I think no one wants to identify the different factors.
Yeah.
These different factors.
Yeah.
Over here. I think these are completely. Yeah, these are completely separate.
Oh, I see. I mean, so suppose that there is a non-trivial intersection between H and RB. Does that change the argument? Your forthcoming, maybe I should wait, but
Yeah. So why did I say that the purifier was entirely in R and not in H? So I don't know the exact argument, but the quantum information people say it's true, and I think it just follows from the fact that R is the much bigger system. But in this typical state.
yeah, okay, so that's fine. Maybe it's one thing for it. But where in your following argument do you use that? Is it crucial,
Well,
or?
if the purifier of B were partially in H, then
So that's
RB
maybe still true, right?
this would still be true if
By
I
definition.
interpreted RB as having a part of
Yes,
H,
yes.
but then I wouldn't know what to do over here.
I
Because
see.
over here I don't know where H is.
I see.
I want to say that the purifier of B is in RB so that I can still identify it over
I
here.
see.
So that's a good point. I mean, these kinds of caveats are always nice to point out. All right, so now we're going to use strong subadditivity over here. Okay, so I'll remind you what strong subadditivity looks like. So SAB plus SBRB. So we're going to use strong subadditivity on this system ABRB. Okay, which is sort of so we're going to trace out everything that's not AB and RB. And we're going to use strong subadditivity on that. Bigger than or equal to S, AB, RB, plus SB. Okay, that's strong subadditivity inequality. So I want to use this fact here to set this equal to 0. Okay, or at least approximately 0, where the others are going to be large. Yeah. All right. Step number 2 is I want to use regular subadditivity plus another inequality which hasn't been used yet. So regular subadditivity applied to the A and then BRB subsystems says this. So subadditivity is used when you have two systems. In this case, the two systems are A and BRB. Yeah. So here's subadditivity. And then there's another inequality, which I think hasn't been mentioned yet, but bounds this, it's sort of bounds, it's like subadditivity, but it bounds in the other direction, and involves the difference of two entropies. Absolute boundary. So this is a somewhat fancier inequality, but it's another one of these universal inequalities. Okay, but now we use this fact again about SBRB being 0. Find this is 0, and this is 0. So SABRB is actually equal to SA, because it's bounded on both sides by the same. Third question?
I think the argument why RB is inside of B is because the way you create the radiation is by reproducing. So you can imagine each qubit that's part of R as being maximally entangled with something that's inside of the black hole.
Sure.
But if the radiation is a large chunk, then you saturate all the bridges, and then there's for each bit inside the black hole, it's maximally entangled with something outside. So that's why it has to be inside of B, because there's no room for entanglement between H and B.
Well,
Well, most of the entanglement comes from interaction with R. I think that's the argument that people give.
But
So-
there could be a still small chunk which is inside H, isn't it?
Well-
I agree that majority of RB should be in R.
But the point is that each bit in R is maximally entangled with something that was inside the black hole.
Monogamy of entanglement.
It's maximally entangled because that's how you create the state. You create pairs that are maximally entangled. So then it means that all of them have to be maximally entangled with it in the maximal way. And the maximal way is, when R is much larger than HV, is that all of them are entangled with R.
Yeah, so I mean, I think that that argument is essentially the same kind of argument that I'm making over here in a different context. Well, the argument that the purifier of B is inside of RB actually depends on the pair production process in an important way, then some people might argue with it if they have some more exotic process by which entanglement is, or by which information gets out. But I do think that at the end of the day, there should be some kind of argument that involves, some monogamy of entanglement type of argument, together with the fact that R is the much bigger subsystem, which tells you that most of the time, unless you're in a very special state, the purifier of RB has to be inside of the purifier of B has to be inside of R. It sort of fits the intuition that when you have a Hilbert space where one of the factors of the Hilbert space is really big, sort of all of the action happens in that factor. Typically. All right, so I want to put together these kinds of inequalities here, right? So we put together, so now we have SAB is bigger than or equal to, this is 0, SABRB is SA, and then there's plus SB. All right, great. So this again looks like subadditivity, except it's going the wrong way. So subadditivity again gives us the other side. So now we know that SAB is equal to SA plus SB, okay? And there's another one of these facts about entanglement, that when you have equality between SAB, SA plus SB and SAB, this, so SAB equals SA plus SB. This means that the density matrix, rho AB, is actually a product state. Okay. But this is entirely unexpected from the point of view of, the Hawking radiation derivation, because these A and B, right? If you're this guy falling across the horizon, you don't really. I mean, you would like to not care about the early radiation. You would like the horizon to be just a piece of flat space with entanglement across the horizon. We don't even need to know anything fancy about Hawking radiation. We just expect that for some piece of field inside the horizon, just outside the horizon, should be entangled with a piece of field on the inside of the horizon. Just in quantum field theory, there's local entanglements in the vacuum. Yeah? But that's in conflict with this. The fact that they're in a product state. That means they're not entangled. Okay, so that's bad. That's the conflict. Basically, the intuition is that the entanglement of B, in order for smoothness of the horizon to happen, you need A and B to be entangled. But the fact that most of the Hawking radiation is already on the outside means that A and R are already maximally entangled. So monogamy of entanglement tells you that A and B cannot be entangled. So that's the conflict. All right, so what's the resolution? I mean, you could say every step in this argument was correct, and that, yes, in fact, A and B are not entangled. What does that mean? That's the firewall. Okay, that means when you're crossing this horizon here, you don't actually see the vacuum locally, and this is a huge perturbation on the vacuum. Okay, it's not really a perturbation anymore. It means something really bad happened, and you run into the firewall and die. The other option is that some kind of assumption here was wrong. So what are the